All right, next up, number 14 here. So for this one, we have the half-life of radium is 1,600 years, and we have a 22 milligram sample. So I'm going to use my exponential decay model with my half-life formula there to tell me R. And so for part A, I'm just going to set up my formula. So I'm going to say mass after time t equals my initial mass, which is 22. And then we'll do e to the negative ln2 over 1,600 times t. So that's just my answer for part A, really just setting up the functions. And it says how much of the sample will remain after 4,000 years. So I do need to be careful on units here. I see that my units were in years to start with, so I'm just going to, I can just use 4,000 then. And so that means I'm going to plug in 4,000 in here for t. Like so. Okay, so that'll be my my calculation there. So I just got to type all of this in. E to the negative ln2 divided by 1,600 times 4,000. All right, so this comes out to 3.889 milligrams. All right, next up for part C, how long until only 18 remains? So I'm going to go back to my original function, but now I'm plugging in 18 for mass. And I'm going to solve for t. And so the first thing I need to do is I need to divide this by 22 to isolate the base. And then I'm ready to switch it into log form. So since our base is e, that's going to be a natural log of 18 over 22 equals negative ln2 over 1,600 times t. And then my last step before I type it in the calculator, I'm going to go ahead and just isolate t here by multiplying by 1,600 over negative ln2. So that'll cancel out on this side, and so I just have to type kind of all of this into the calculator and see what I get. I got 1,600 divided by negative ln2, and then times ln of 18 over 22, and that tells me that it's 463.2, and this is going to be in that consistent units of time, which is years. All right, next up here we got number 16. So this one is giving us the equation already. And so then it just says how much will remain after 60 days. It does say that time is in days on this. So that just means for part A, I'm just going to plug in 60. So it'll be m of 60 equals 40 times e to the negative 0.0277 times 60. And I don't need logs for this. I know everything on that right-hand side, so I can just type it into my calculator just like that. And that is 7.59. And this is in grams because that was just the units given. Okay, and so next up, part B, it says how long until 10 grams remains. So that, again, is asking me to go back to the original function and plug in 10 here. So I'm going to say 10 equals 40 times e to the negative 0.0277 t. I need to divide by 40 first to isolate my base of e. So then I can reduce this to 1 over 4 equals e to the negative 0.0277 t. And now I'm ready to switch it into log form. Since it's base e, it's going to be ln of 1/4 equals e to the, oh no, not e. E is the base. It equals negative 0.0277 t. So then I'll just divide by negative 0.0277, both sides, of course. Type that in and get my answer. And that will be 50.05, we'll call it, and that will be years. Oh, no, it's not. It's days. Excuse me. Awesome. All right, so that's it for part B. And then lastly, we have part C. So for part C, it says, what is the half-life of this element? Couple different ways we can solve this. I see here, and the way I would probably do this is looking at that exponent and kind of matching it up with our exponential decay model. I see here that R is actually 0.0277. It is not, R is not negative 0.0227 because it says here we have negative R, so the R is the positive version of that number. And so now if I use this formula, it would say that 0.0277 equals ln2 over h. So this allows me to solve for the half-life. I would first multiply the h over, and then I would divide both sides by 0.0277. So that means the half-life is going to equal ln2 divided by 0.0277. So that's going to be 25.02. And the units on this half-life is a time, and so this is going to be that same consistent days here. All right, here we have number 17. I'm going to go to the next page and do number 18. All right, next up we got number 18 here. So this one says our radium-221 has a half-life of, I actually can't see that. Okay, it says 30 seconds. So how long will it take for 95% of the sample to decay? So I'm going to build my exponential decay model here. So I'm going to say m of t equals, and then m sub 0, we'll talk about that in a second, but I know this is negative ln2 over 30 seconds, and then times t. And so what I would say here is that when it says 95% of it to decay, you can kind of start with whatever you want here. I'm actually going to go ahead and say, well, let's start with 1 gram. And if we start with 1 gram, if 95% decays, that means that actually only 5% is left. So it's like 95% of it is gone, so 5% of it is left, and that would be 0.05 if we started with 1. And then up here I'll do negative ln2 over 30 times t. So I can actually just scribble out this 1. I'm really dividing both sides by 1, but it's not really necessary with 1. That's why I like to start with 1 if the initial mass is not given. If it's just talking about percentages, I always use a 1. So now that I scribble out that 1, I'm actually ready to switch it into log form. So it'll be ln of 0.05 equals negative ln2 over 30 times t. And then I would just multiply both sides by 30 over negative ln2. 30 over negative ln2. All right, and so those cross off, so I get t equals, and so I get 30 over negative ln2 times ln of 0.05. And if I do that, I get 129.66, and this is in seconds. So there you go. All right, next up here, it says after 3 days, a sample of radon-22 has decayed to 58% of its original amount, and it asks you what's the half-life. So how I would set this up is I would use this model, and so kind of like last time, it says 58% of its original amount. That actually means that we can use the 0.58 there if we started with 1. So that's what I'm going to do there. And then I'll put E. I don't know what R is, but I know that T is going to be 3 days. So I'm going to use this to figure out what R is, and then I'm going to use R to figure out the half-life. I can actually, again, scribble out this 1, so then switch it into natural log form. ln of 0.58 equals negative 3R, and we'll divide that by negative 3. So R equals ln 0.58 divided by negative 3. So that's 0.1816, let's call it. Now that is R, but that is not the half-life. I can use, though, the half-life formula to now solve for that. So I know that 0.1816 equals ln2 over h. So anytime I know what R is, I can use that to multiply the h over, and I'll divide that 0.1816 back over to this side. And so that gives me h as ln2 divided by 0.1816. Which would be half-life at about 3.817 days. All right, and then so next up, part B, it asked us how long would it take for the sample to decay 20% of its original amount. So once again, when it says of, I'm actually going to use that 0.2 right there, and I'll use 1 right there. And then we have E, and then we now know R is negative, or actually R is 0.1816, but I'm going to put negative R. So I'm just using this right here. You could use ln2 over the half-life, but I know what R is anyway, so I'm just going to use that. We'll put a T right there. I'll scribble out the 1, and we get ln of 0.2, excuse me, equals negative 0.1816 T. So we'll just divide by negative 0.1816, both sides. So T equals 8.86. And This is in, once again, days. All right, and last up here we have some carbon dating. So same idea here. It says this one contains 59% of the carbon-14 it contained originally. So when that happens, I'm going to put 0.59 here because it's of. It doesn't. That's not how much is gone. That's how much is left. Put a 1 right there, and then we have e to the negative ln2 over our half-life, which is 5730. I'll put the time right there. Okay, so then we'll scribble this out, and then we'll switch this into log form. So ln of 0.59 equals this whole exponent, which is no longer an exponent. And then I'll just multiply by the reciprocal here, 5730 divided by negative ln2 to both sides. All right, we'll cancel that out, and t equals 5730 divided by negative ln2 times ln of 0.59, and so that'll be 4361.75 years.